Okay, so we're going to be doing the derivatives of trig functions today. So I'm going to start with just a simple trig function. So we'll take f of x is equal to sine of x, right? And we're just going to find this derivative just using some pretty simple observation of a sine graph, okay? So if I want to graph the sine function, okay, everybody knows that at 0, sine is 0. But what's my next important place on the sine function? Yeah, it's at pi over 2 is where I get a 1 for my value. And then next, I go to pi. What's the sine of pi? 0. All right, and then next is 3 pi over 2. And at 3 pi over 2, sine is -1. And then back at 2 pi, and sine will be 0, right? So this is what, a sketch of the sine graph would look like, right? And we could just keep it going. And so I want to sketch now f prime of x. So we're going to sketch the graph of its derivative. And then I just want to see if you can recognize it, okay? So if we start working through here, actually trying to sketch the graph of a derivative, right? So we're doing what we did last week, right? Where we have a graph of a function and we want to graph its derivative. So there's some key points, right? At pi over 2, you can see at the very top of this graph at pi over 2, what would you say the derivative is? Yeah, the derivative is 0 because it flattens out up there. And then at 3 pi over 2, you're at the very bottom, so you can see that the derivative there would also be 0. Then it would hit 0 again, right? And since this thing is a wave, it's going to keep going like that. Now, does anybody remember? We also want to talk about the slope at 0. Okay, the slope at 0 is going to be really important. But before we do that, does anybody remember the limit as x approaches 0 of sine x over x? It's 1. Okay, now we had a really long discussion about the fact that it's 1. Does anybody remember why it's 1? Very good. So Matt's saying that whenever we get really close to 0, what happens is the sine function begins to give you back whatever you put into it. Okay, and do you remember taking the graph of the sine function? We took the graph and we zoomed in really, really close to it. What did it look like when we zoomed in on it around 0? Yeah, it looked like a straight line, okay? What line did it look like? Yeah, it looks like the line y equals x whenever you zoom in really, really close, okay? So right around 0, it looks like this right here. So what would you say the slope is around 0? 1. Yeah, the derivative of x would just be 1. So whenever you're really, really close to 0, the sine graph actually has a slope of 1 at that point. So if I move over to pi, what do you think the slope is at pi? Very good. It's -1 because it's the same slope, except instead of going up like we were at 0, over here at pi, we're going down. All right, what about 2 pi? What would you say the slope is at 2 pi? Yeah, it's a 1 again, and it just continues. So it looks like this. Now, and this blue graph would just keep going. Right? And so we could just keep it going all the way across if we wanted to. But does anyone recognize that blue graph? That is exactly right. That's the graph of cosine. So it turns out that the derivative of sine is cosine. Okay? So that's an important concept. You need to put that in your notes. Right, here's the big idea that we're going for. The derivative of sine is cosine. We'll check. Okay. Does everybody have this written down? Yeah? Okay. Well, let me go to the next page. And so now Marshall is asking if the same is, if the reverse is true. So let's actually talk about the cosine graph, right? The cosine graph starts at 1 when you're at 0, right? And then when you go to pi over 2, cosine hits 0, and then at pi, cosine goes down to -1. At 3 pi over 2, cosine's back up to 0, and then at 2 pi, cosine's back up to 1, right? And it just continues that way. This is how the cosine curve looks. And so the cosine curve just simply goes like that. And so now, let me do this just for a little help on these endpoints, right? The thing starts to drop afterwards on both of those. All right, so now if we start graphing the derivative of cosine, I'm going to graph it in blue. You can see right here when our x value is 0, we reach a peak. So the cosine graph would have a derivative of 0 at that point. And at pi, you reach the very bottom of a valley. So it would have a derivative of 0 at that point. Now, when you look at pi over 2, okay, look at cosine's slope at pi over 2. What would you say about it? You know it's negative because it's going down, and it works just like sine does. So all of those points where sine, when it was going down, the steepest the cosine slope actually ever gets is 1 or -1, okay? So in this case right here, when we're at that point where we know it's going down, it actually has a slope of exactly -1 at that point. Now at 3 pi over 2, what kind of slope is it going to have? It's going to have a +1. And then at 2 pi, you can see that it's reached a peak again, right? And so it's going to be at 0. Now, what does that graph look like? Sine almost, right? Because if you notice the sine function actually starts off at 0 and goes which way? Up. This one that we just graphed in blue right here is starting off at 0 and going down. So how does that happen? It's negative sine, right? Changes the direction that it moves in. So the big takeaway here is simply that the derivative of cosine is negative sine. Okay. The derivative of cosine is negative sine. Okay. The derivative of cosine is negative sine. Now we have 4 other trig functions, right? But they're a little bit harder to get if you just kind of look at their graphs. So we're actually going to derive the 4 other trig functions. So I'm going to do some work, and I want you to keep up with me because it's something that I think is pretty simple and you can understand, right? And we're going to take big takeaways, though, right? So this is the big takeaway. You need to make sure that you kind of have that highlighted in your notes, and you also need to have this right here highlighted in your notes. Those are the 2 big ideas that we're going for. So from now on, we don't have to draw graphs and go through the whole process, right? We just know now when we take the derivative of sine, we get cosine. When we take the derivative of cosine, we get negative sine. Now the next one I want to talk about would be, anybody? Tangent, yeah, tangent x. Okay, so we want to take the derivative of tangent x. Do you know the derivative of tangent? No, not off the top of your head. I haven't told you what the derivative of tangent is yet, right? How are you supposed to know if I haven't told you? But what do you actually know the derivative of right now? What trig functions? Sine and cosine, because we just did those. So what can you do with tangent? Very good. Tangent is the same thing as sine x over cosine x. Now, can you take the derivative of this? Yes, you can take the derivative of this by using the quotient rule. Very good. Okay? So here's what I'm going to do. I'm going to use the quotient rule, and I'm going to end up getting an answer, and then once we get the answer, it will always be the same, so we can just memorize it at that point. And whenever we see tangent again, we don't have to go through this process again. We can just know that tangent is going to be this. But let's actually use this process and discover what the derivative is going to be. What does the quotient rule say? Yeah. Low d high minus high d low all over low squared. So we're going to start with the bottom. So here's our low, the denominator, times the derivative of the top. And so the top is sine. What's the derivative of sine? Cosine. Minus high. So the top part, our numerator here is sine d low. What's the derivative of the bottom? Yeah, the bottom is cosine, and the derivative of cosine is negative sine all over low squared. Now, cosine times cosine, what does that make? Okay, so that becomes cosine squared x, multiplying these two cosines together. Then notice we have a negative sign times a negative sign. Yeah, a negative times a negative is going to make a positive, and sine times sine makes sine squared x all over cosine squared x. Very good. This top part is actually a trigonometric identity, right? It's one of the Pythagorean identities. And the Pythagorean identities say that sine squared plus cosine squared, or you could have it this way, cosine squared plus sine squared is equal to 1. So this top is exactly always equal to 1. So I'm going to change the top to 1. Very good. 1 over cosine is the same thing as secant. Remember, that's a trig identity. 1 over cosine is equal to secant x. But this isn't just 1 over cosine. It's 1 over cosine squared. So when I use the identity, it's going to make secant squared. Very good. Secant squared x. So here's our final answer. So this is the big takeaway, right? We started by taking the derivative of tangent x, and we ended with secant squared x, right? That is the main idea, right? So the derivative of tangent is secant squared. All right, so let's pick another trig function here. Secant. All right, so let's actually do secant now. Secant. D dx secant x. All right, so we want the derivative of secant, but we don't know how to just do secant by itself, so we're going to derive it. Very good. We want to use sines and cosines because we know those right now. Okay, so we're going to change this. Remember, secant is the same thing as 1 over cosine. And now I'm going to take the derivative of 1 over cosine using the quotient rule. Yeah. So the quotient rule tells me to do the bottom, so times the derivative of the top. What's the derivative of the top? 0. Minus the top, 1, times the derivative of the bottom. What's the derivative of cosine? Okay, times negative sine x. All over the bottom squared. So cosine times 0 is just going to disappear. It's going to cancel, right? And we have a negative 1 times a negative sine. So that's going to make sine x over cosine squared x. Yes. Right? Now, with this right here, okay, what I'm going to do is I'm going to do a little math magic right now, okay? It's not overly complicated, but this cosine squared is the same thing as cosine times cosine, right? Is everybody okay with that? It's a pretty simple idea. You're squaring the thing, right? So I'm going to change this into two fractions that are being multiplied together. And on the first one, I'm going to put cosine of x on bottom and a 1 on top. And on the next one, I'm going to put sine of x on bottom and a cosine x on, or sorry, sine of x on top and a cosine x on bottom. Now, does everybody agree with the fact that what I've written down right here, okay, is the same as what I have up here, right? Because if we do top times top, we're going to get sine. And if we do bottom times bottom, we're going to get cosine squared. So now I'm just going to transform these things right here. 1 over cosine is the same as what? Secant. So this is secant x times, yeah, and sine over cosine is tangent x. Okay, so here's our big takeaway. The derivative of secant is equal to secant tangent, right? The derivative of secant is secant tangent. How would you graph the derivative? Well, this graph is actually going to be pretty complicated. Yeah, because the graph of secant, um, it looks like the u's that go up and down, right? So the graph of the derivative is secant times tangent. It works out, but the graph of the derivative is actually going to look pretty different. So it's going to, for this one in particular, it's going to hit 0 right here. But these are, big negative slopes going into big positive slopes. So it's going to go from like a huge negative to a huge positive, kind of along with that one. And they'll work out, but they kind of adjust a little bit at each different spot because it goes from huge positives. This one goes from huge positive slope to huge negative slope. So it's actually going to come from this way. And it won't go that far over. It'll be more like this, right? So they'll just keep flip-flopping like that in order to stay with everything. Okay. All right, so let's do the other two trig functions really quick. So we've done sine, cosine, tangent, and then we've done secant. What else do we have? Cosecant. Okay, so let's do the derivative of cosecant. Okay, to pull this one off, the first thing I'm going to do is change cosecant into what? 1 over sine x. And I'm going to use the quotient rule here. So the bottom, so low, sine of x, times the derivative of the top, which is 0, right? Because the derivative of a constant is always 0, minus the top times the derivative of the bottom. Now, what's the derivative of the bottom is going to be what? Cosine. All over the bottom squared. Well, this right here is going to be 0, right? Sine of x times 0 is just going to disappear. And so we have negative cosine x over sine squared x. And I'm going to do the exact same thing I did last time. I'm going to break this into two fractions that are being multiplied together. And the first one, I'm going to use a negative 1 over sine x. And the second one, I'm going to use cosine x over sine x. Right? So if I multiplied them straight across, top times top would give me negative cosine, and bottom times bottom would give me sine squared, right? So I'm just kind of breaking this thing up. Now, what is 1 over sine? Yeah, it's cosecant, and we have a negative 1 over sine, so that's going to be negative cosecant. Times, what is cosine over sine? Cotangent. Okay, so big takeaway is that, the derivative of cosecant is equal to negative cosecant cotangent. Might as well do cotangent, right? All right, so let's do the derivative of cotangent. So I'm going to start by changing this thing into sines and cosines, right? Because I know their derivatives, that's no problem. What's the derivative? All right, so what does cotangent actually change into? Very good. It is cosine over sine. And cotangent is equivalent to cosine over sine. And so now if I use the quotient rule, stick with it, low, so we got the denominator, we just write it down without doing anything, d high, so we actually need to take the derivative of the top. And what is the derivative of cosine? Yeah, it's negative sine minus high, well the top is cosine, d low, so the derivative of the bottom. What's the derivative of the bottom? Yeah, it's cosine. The derivative of sine is cosine all over the bottom squared. So sine squared. So sine times negative sine. So make negative sine squared, right? And then we have negative cosine times cosine, so that's going to make negative cosine squared. All over sine squared. Now, whenever we did tangent, remember we had we had sine squared plus cosine squared was 1. So now, if we have negative sine squared minus cosine squared, what do you think that is? Negative 1. That's exactly right. Since they're both negatives, right? If they're both positive, it gives you positive 1. If they're both negative, it gives you negative 1. If one's positive and one's negative, you don't know anything, okay? But if they're both negative, it's a negative 1. If they're both positive, it's a positive 1. So this is negative 1 over sine squared. Yes, 1 over sine is equivalent to cosecant, right? That's one of our reciprocal identities. 1 over sine is cosecant, okay? But right now we have a negative 1 over a sine squared. So what we're going to end up with is a negative cosecant squared x, okay? So negative cosecant squared. So there's the big idea, is that the derivative of cotangent is equal to negative cosecant squared. Okay, so we don't have to actually go through and derive them anymore, although I may ask you to for some bonus points, right? But we can just memorize them now. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of secant is secant tangent. The derivative of cosecant is negative cosecant cotangent, and the derivative of cotangent is negative cosecant squared. You're just going to have to, you're going to deal with them enough to where you've memorized them. You will memorize them all, and you'll deal with them enough to where they'll just stick, hopefully, right? Okay, so now let's actually work a few problems. Okay, we're going to work a few problems using trig functions. So if you want to flip in your textbooks to page 147, go ahead and go to page 147. I'm sorry, 167. 167. One 167. All right, and let's look at number 2. Okay, so we're actually going to work number 2 off of page 167. And it gives us the function y equals cosine of x. And it wants us to find the equation of the tangent line at pi over 3. So the equation of the tangent line at pi over 3. Remember, when we're looking for the equation of a line, we need two things. We need a point and we need a slope. So the first thing I want to do is get a point. So we know our x value for the point is going to be pi over 3. But how do I get a y value? Yeah, just plug it into this equation right now. So y is equal to the cosine of pi over 3. You can see when I get this answer, it will be equal to a y value. Now, what is the cosine of pi over 3? All right, does anybody remember what pi over 3, what kind of angle does pi over 3 make? Change it from radians into degrees. 60, right? Yeah, pi over 3 is 60. Remember, the rule is pi over 3 goes to 60 degrees, pi over 6 goes to 30 degrees, and pi over 4 goes to 45 degrees, right? Okay, so I'm going to draw a 30, 60, 90 triangle. So 30, remember, which is the same thing as pi over 6. 60, which is the same thing as pi over 3, and then 90. Now the sides of a 30, 60, 90 triangle, right? Opposite the 30 goes a 1. Opposite of the 60 goes a square root of 3, and the hypotenuse is 2. Got to remember these special right triangles. Okay. So the cosine of pi over 3, so we're trying to work from the pi over 3 angle, right? Which is this one down here, the 60 degree or pi over 3 angle. And cosine, what's the, using SOHCAHTOA, what do you actually use for cosine? Adjacent over hypotenuse, right? Adjacent over hypotenuse. So adjacent is the 1, and the hypotenuse is the 2. So y is equal to 1/2. So here's our point, right? That's really important. Okay, now we need a slope. And remember, a derivative is a slope. That's what it's going to tell us all about slopes. So let's take the derivative. What's the derivative of cosine? Negative sine. Okay? So now if we actually want to find the slope at pi over 3, then what we're looking for is the negative of the sine of pi over 3, right? We're going to plug it in and find the slope. Well, it's convenient for us. We already have our triangle drawn, right? And we're still talking about the pi over 3 or 60 degree angle, so we're still working from down here. But now we want the sine value, right? We want the sine value. According to SOHCAHTOA, what does sine give you? Opposite over hypotenuse. So opposite is the square root of 3. And I'm keeping that negative sign out front, right? And the hypotenuse is 2. Okay? So here's our slope. Negative square root of 3 over 2. So I'm going to take the point and the slope, and I'm going to use point-slope formula, right? So y minus y1, that's 1/2, is equal to m, that's negative square root of 3 over 2, times x minus x1. And x1 in this case is pi over 3. And now I'm just going to simplify this thing out. So 1/2 equals, and then I'm going to distribute here, right? I'm going to multiply. Well, the negative square root of 3 over 2 times x just makes negative square root of 3 over 2 times x, right? Negative square root of 3 over 2 times negative pi over 3 requires a little more work, right? Top times top. Well, first off, the negative times the negative is just going to make this thing positive. And then I'm doing top times top. What's the square root of 3 times pi? Yeah, that's correct. It is just the square root of 3 times pi, or if you want to change the order, you can. Pi times the square root of 3, either way. And then bottom times bottom, 2 times 3 makes 6. Okay, so now to get y by itself, I need to add a 1/2 on both sides. So these cancel, and I get y is equal to the negative square root of 3 over 2 plus, okay, now this back part requires a little bit of simplification. What 1/2, I want a common denominator so that I can add. So what is 1/2 equivalent to? Yeah, it's the same as 3/6, right? So I got a common denominator of 6. And on top, I have pi times the square root of 3 plus 3. Do you know how I write that? Pi times the square root of 3 plus 3. Right? There's, oh yeah, don't forget your x behind your slope there, okay? But the back part, you know, it just kind of ends up being that weird looking fraction because there's not a lot of simplification you can do there without having to round, okay? Brandon. Okay, so on the triangle, it doesn't matter which way you draw it. Okay, so you could draw it as, you know, a 30, 60, 90, or you can just go up and draw it, and you could get a 60, 30, 90. That's not what's important. Okay, what's important is that you have 3 side lengths in a 30, 60, 90 triangle. They are 1, the square root of 3, and 2. And in a triangle, the size of a side is proportional to the angle that it's opposite from. That sounds complicated, but the length of a side is proportional to the angle that it's opposite from. And so what I mean is, you know, if we have a triangle and it looks like this, let me see if I can demonstrate this some way using the smartboard, right? Okay, so say I have these 2 lengths right here, and then I'm just going to make a little imaginary line right here, okay? Now, if I make this angle, you know, if I close this thing down, so let me see if I can close it down. Now, that's the same side length, right? Okay, but when it was, you know, the angle was open more, I had this dotted green line right here. Well, now when I close the angle more, guess what happens? It gets smaller to this little blue line. And then if I take it and I close the angle down even more, guess what happens to this opposite side over here? It gets even smaller. So if an angle opens up really big, the opposite side gets bigger. And if it closes down really small, the opposite side gets smaller. So with that in mind, these are in order, right? By the way, 1 is smaller than the square root of 3, which is smaller than 2. Okay? So what's important is that if the 1 is the smallest number, it should go opposite of the smallest angle. So the 1 has to be opposite of the 30. The root of 3 is middle, so it has to go opposite of the 60. And the 2 is the biggest, so it has to be the hypotenuse. Notice the hypotenuse is always opposite of a 90, and it's always the longest side. Because if you have a 90-degree angle in a triangle, it has to be the largest angle. So the largest side has to go opposite the largest angle. So, 3 and 2, is that just always? It's the proportions that they always keep. Okay? Now, opposite of the 30 on this other one has to go the 1. Opposite of the 60 has to go the square root of 3, and the 2 has to be the hypotenuse. So both of these triangles are correct, okay? Because if you go opposite the 30 on both of them, there's the 1. And opposite the 60 is the square root of 3. That's the important thing. It doesn't matter that you draw the 30 at the top or the 60 at the top or anything like that. Okay? Does that answer your question? Yeah. Okay. I know. It'll be a good trig review for everybody in second block as well. So. All right, let's look at number 4 together. Y equals secant x at x equals pi over 6. So this is number 4. And we're trying to write the equation of a tangent line again. Right, the equation of a tangent line. So the first thing I need to do is get a point. Well, I know my x is pi over 6. And y is going to be equal to the secant of pi over 6. What kind of angle is pi over 6? 30 degrees. So I'm going to come over here and I'm going to draw myself a 30, 60, 90. And so as we just discussed, right, opposite of the 30 has to go a 1. Opposite of the 60 has to go the square root of 3. And opposite of the 90 has to go the 2. Now we're looking for secant. Does anybody know? Secant is cosine flipped, right? So cosine is equal to the adjacent over the hypotenuse. So secant is cosine flipped. It's going to be the hypotenuse over adjacent, right? Hypotenuse over adjacent. Now, this thing says pi over 6, which is what angle? 30. So we have to work from the 30-degree angle, okay? From the 30-degree angle. And we want hypotenuse over adjacent. So the hypotenuse is 2. There it is. And the adjacent side is so the square root of 3. So 2 over the square root of 3. And I'm going to leave it with the square root of 3 on bottom. I know that's something that you didn't do in trig, but I'm not concerned about it here. No. I mean, we may want to change it later. Actually, when it comes to using our point slope formula, it'll make things easier on us if we do go ahead and rationalize the denominator. Okay, so let me multiply by the square root of 3 over the square root of 3, which is really multiplying by what? 1, right? Exactly. It's like multiplying by 1, so does it change the value? No? Have you wondered why you did that in trig? Just did it anyway? No, you're multiplying by 1. Remember, that doesn't change anything. So 2 times the square root of 3 over 3. Okay, so there we go. We rationalized our denominator. Now, to get the slope, we need a derivative. So y prime. What's the derivative of secant? Okay, so secant x times tangent x. Good, secant tangent. Now, we need to plug in so that we can find the slope at this particular point, right? We got our point. We want the slope at that point, so we're going to plug in for that x value, pi over 6, tangent of pi over 6. Now, what is the secant of pi over 6? Yeah, we did that right here, didn't we? All of this stuff was doing the secant of pi over 6, and we got 2 square roots of 3 over 3. So let's go ahead and use that since we've already done it. And then we need the tangent of pi over 6. So I'm going to come back to our triangle and the 30-degree angle, right, which is pi over 6. And we're going to use tangent. Now, what's tangent's ratio? Yeah, tangent is opposite over adjacent. So opposite is the 1, and adjacent is the square root of 3. Now, let me just make this note. I'm going to come back up here. Well, I'm not going to do that. I'm going to just go ahead and work it out this way. I don't want to confuse anyone, so I'll just work it out this way. So let me just multiply top times top, so that'll be 2 square roots of 3 over bottom times bottom will be 3 square roots of 3. Does anybody see anything we could do there? Yeah, the square root of 3 on top and on bottom will cancel one another out. Well, it's like having 2x over 3x. The x's do what? Cancel. Why not rationalize it first? Okay, well, let's rationalize it first. What am I going to multiply by, Brandon? Square root of 3 over the square root of 3. So this is, on top, I get 2 times. Now, what's the square root of 3 times the square root of 3? 3. Yeah. It's like saying, remember, multiplying something by itself is the same thing as squaring it. 3 times 3 is 3 squared. Okay? So when you do the square root of 3 times the square root of 3, what you're saying is, I want to square the square root of 3. Yeah, and they're inverse operations. So whatever's inside just comes right out. Yeah. Now on bottom, I have 3 times, and the square root of 3 times the square root of 3 is 3, right? So what I did was I just combined those two things, right? So I left the 2, and the square root of 3 times the square root of 3 gave me 3. I left the 3, and the square root of 3 times the square root of 3 gave me 3. Okay? So now, Brandon, what's 2 times 3? What's 3 times 3? Which is 2/3, right? So as you're just, by not going ahead and just canceling the 2 square roots, you're giving yourself more work to get to the same answer. Okay? It's the same thing. That's why it all works out like that. Okay? All right, so here's my slope. M is equal to 2/3. That's what we were just trying to find. was the slope, right? Okay, so I'm going to try to get it right here where I can see both of them. Here's my point. It was up there. And here's my slope. It was 2/3. So y minus y1, you can come up here and see that my y value was 2 square roots of 3/3, is equal to m, that's 2/3, times x minus x1, yeah, which is pi over 6. Okay, so y minus 2 square roots of 3/3 is equal to 2/3 x minus, yeah, and do top times top, so 2 times pi makes 2 pi, and 3 times 6 makes 18. Okay, so I'm going to simplify this fraction in the back before I move on, right? Because notice there's a 2 on top and an 18 on bottom, so 2 will go into both of them. So y minus 2 square roots of 3/3 is equal to 2/3 x minus pi over 9, right? 2 will go into the top. So it cancels out the 2 on top, and on bottom, 18 divided by 2 makes 9. And now I'm going to add. So y equals 2/3 x minus pi over 9, and I'm going to add the 2 square roots of 3/3. Now I need to get a common denominator, so that's going to be 9, right? So what do I need to do to this 3 to turn it into a 9? Times 3. So what should I do to the top? Oh, look, and if I multiply by 3/3, that's the same thing as 1. So I haven't changed the value again, right? Do you guys realize how often you multiply by 1 and didn't know what you were doing? Okay, you're multiplying by 1 a lot in order to change the way things look. So y is equal to 2/3 x minus pi over 9 plus 3 times 2 makes 6 square roots of 3/9. So I'm just going to rewrite it one last time as 2/3 x minus, and I'm going to combine this back stuff into one fraction, right? It's pi plus 6 square roots of 3 all over 9. We're done. Well, you're going to get your chance to try at home on numbers 1 and 3, right? They're going to be part of your homework. So study your notes, okay? All right.
It's maybe because at the very top you plugged in pi over 6.
Uh-huh.
And then it seems like you just kind of forgot that part, like it didn't have it. You just used the numbers off the triangle. Did I miss that?
Pi over 6 is the same thing as a 30-degree angle.
Okay.
So what I did was I drew a classic 30, 60, 90 triangle. And pi over 6 is the same thing as 30. So I just worked from the 30-degree angle. And we were trying to find secant. And secant's ratio is that you find the hypotenuse and put it over the adjacent from the angle that you're talking about. So we're talking about this angle. So I found the hypotenuse of the triangle, which is 2. And I put it over the adjacent angle, or the one right next to it, and that was the square root of 3. So that's the answer. That's where the answer for secant of pi over 6 came from. Yeah, I need to use the triangle to get that answer. Unless you have them memorized, you can just write it down. It's perfectly fine. Marshall. What I do to rationalize right here, I had 2 square roots of 3 over 3 square roots of 3. Down more?
Yeah.
All right, I didn't do any rationalizing here. Are you talking about adding these two fractions right here? Okay, I didn't rationalize anything, but in order to add these two fractions, I need a common denominator. And so my least common denominator would be 9. So what I need to do is multiply this 3 by 3 in order to turn the denominator into a 9.
But I thought it was pi over 6. It was, but when you added...
It was pi over 6 up here, right? But then when I distributed this 2/3, it became 2 pi over 18. And then the 2 over 18, I simplified to 1 over 9. So instead of 2 pi over 18, it became 1 pi over 9. Does that clear it up? Okay. All right, let's look at some examples in your textbook of just taking some more complicated derivatives. Okay, so no equations of tangent lines here. We're just going to do some derivatives. So we'll start with number 12. Okay, so go to number 12 in your textbook. Yes, still on page 167. K of theta is equal to theta squared times sine squared of theta.
You're just gonna treat theta as a variable, right?
Yeah, theta is the variable. Yeah, it's like theta is x in this case. Yeah. By sine squared. Now, do you know how to do sine squared? Do you know how to do a function raised to the second power? What's the derivative of sine squared? Right? You don't know how to do this. You don't know how to do that, right? So what could you change it to make it something that you do know how to do? What does it mean to square a number? Oh, so I could change this into theta squared times sine of theta times sine of theta. Right? This right here is sine squared. It's sine times sine. But since you don't know how to do sine squared yet, you can go ahead and break it apart to sine times sine. And you're going to have to use, what rule would we use here? It is a product rule. And notice there are how many pieces to it? Yeah, there are 3 pieces to a product rule here. So what do we need to do? Yeah, we got to combine 2 of them. Now I'll let you choose. Which ones do you want to combine? Okay, so we're going to combine these 2 in the back. And we're going to use a product rule within a product rule here. Because we have 3 numbers being multiplied together. By the way, that is the only way for you to be able to do this right now. Okay, you have to change that sine squared into sine times sine. So K prime is going to be equal to the first times the derivative of the second. Well, the derivative of that second stuff, that's the hard part, right? So we'll come over here and we want to take the derivative of this piece right here. And the way you take the derivative of 2 things being multiplied together is you write down the first piece and multiply times the derivative of the second. What's the derivative of the second piece? Yeah, the derivative of sine is cosine. Now we want to do the second part, which is sine of theta, right? This one, times the derivative of the first. And the first piece is sine of theta. What's the derivative of sine? Cosine. So look, I have sine of theta, cosine of theta, plus sine of theta, cosine of theta. So what I'm trying to say is that we have a sine cosine and another sine cosine. So I have 2 sine cosines, yeah. Because they're exactly the same. So we can combine like terms, okay? So we're doing the product rule, and we did the first times the derivative of the second. And remember, we came off to the side and did the derivative of this second piece, and we got this, 2 sine theta cosine theta plus the second part, which is, sine theta times sine theta times the derivative of the front piece. What's the derivative of theta squared? Yeah, that's going to be 2 theta. Okay, and I'm just going to clean this up a little bit. So K prime of theta will be equal to, so all of this is being multiplied together. Theta squared, 2 sine theta, and cosine theta. So the most natural way for me to write this is to multiply the 2. I like to put my constants in front. So I'm going to call it 2 theta squared times sine theta cosine theta. Right? Yes. And then this 2 theta I'm going to bring to the front. So 2 theta. And then sine times sine, I'm just going to go ahead and transform it back into sine squared theta. right? I had to make it longer so that I could actually keep using the product rule in order to work this out. But now that I'm finished and I want to simplify it, I'm going to bring it back down.
I don't like that.
Okay, and I'm going to factor out right here just to try to kind of make a point, okay? And so I'm going to look at these two pieces, that piece and that piece, since they're separated by that plus sign. And I want to take out everything that they have in common. So they have a 2 in common, right? They have a theta in common, so I'm going to take out theta. And they have a sine in common. Very good. So if I take out a 2, a theta, and a sine right here, what's left? Yeah, in the front part, there's just a theta and a cosine left. And in the second part, there's just one sine left, right? Because it was sine squared. And so if I took one of them away, now there's only one left, right? And you could have left it in this form right here. I wouldn't make a big deal out of that, right? So either way. Yeah, that's it. Not going to be a lot of simplifying going on from there. All right, so let's look at I'm going to skip down and do number 16 now, okay? So number 16 says this. It says g of z is equal to 1 over tangent of z minus cotangent of z. Okay, so g prime of z, and I'm going to use the quotient rule here. And the quotient rule says we do what? Low D high. Yes, not high D low. It starts off low D high. So low is tangent of z minus cotangent z. And I need to treat that like one piece, right? It's just my low. D high. What's the derivative of the top? 0. So that stuff times 0. Minus high, well, that's 1, times the derivative of the bottom. So the derivative of the bottom, what's the derivative of tangent? Very good. The derivative of tangent is secant squared z minus, what's the derivative of cotangent? Negative cosecant squared z. All over the bottom squared. So this will be tangent z minus cotangent z all squared, right? All squared. So g prime of z. Now this front part is just going to completely disappear because it's being multiplied by 0. So that whole thing goes. Yes. Now I'm going to go ahead and distribute this -1, right? So the -1 times the secant squared is going to make negative secant squared z. And then this was minus a negative cosecant, so that's really plus a cosecant. And now when I distribute the -1, it's going to make negative cosecant squared z. Okay? So we had a triple negative there, which actually is a negative, right? The two negatives to start with turns into positives, and then when I distribute the -1, it actually makes it a negative secant squared of z all over the bottom, which is tangent z minus cotangent z all squared, right? Let's look at number 8. Okay, I'm going to backtrack and look at number 8 right here just to try to, get another point across. Okay, so 8 is f of x is equal to 9 secant x plus 12 cotangent x. Now, f prime of x would be equal to, how do you take the derivative of 9 secant x? You can use the product rule, okay? But there's a more important rule that's called the constant multiplier, okay? And all it says, if you have a constant, all it means is that if you have a constant times something else, then you just write the constant down and then take the derivative of the other part. And I promise you, you've been using this, okay? Because if we had 2x cubed and I wanted you to take the derivative, what you've really been doing is this. 2 times the derivative of x cubed, and now you do the 2 times 3 and get the 6x squared. You've just been skipping that part and going ahead and multiplying the 3 times the 2, okay? And here's why the product rule, you could use the product rule, but it'll be useless, okay? So I'm going to show you why, because it's important for you to know why, okay? But here's why the product rule won't help you in either of these scenarios or this scenario. If you do the first times the derivative of the second, then you get what you already need. But when you do plus the second being the x cubed times the derivative of the first, now if there's a constant in front, the derivative of the first is always going to be 0. And so this second part in the product rule will always disappear because there would be a 0 for the derivative of the front part. And so all you really need to do is just leave the constant and multiply it by the derivative of what's right behind it. Now notice, that's not for a constant that's by itself. A constant by itself goes to 0. But a constant being multiplied by something, you keep and just multiply it by the derivative. So 9 times secant is just 9. And then what is the derivative of secant? Very good. So this would just be 9 times secant x tangent x plus. And now there's a constant 12 in the front, so I just write my 12 down. And then what's the derivative of cotangent? So negative cosecant squared x. So f prime of x is equal to 9 secant x tangent x. And I'll put parentheses around my x's so it doesn't look like I'm just writing random letters, right? And then this 12 is multiplied by a negative cosecant squared, so I'm going to call it negative 12 cosecant squared of x. Your homework for tonight is on page 167. Page 167, and I want you to do numbers 1, 3, and 13 through 23 odd. Okay, so 1, 3, and 13 through 23 the odd on page 167 in your textbook.